This is my Tech Talk, Institute of Aeronautical Engineering, Autonomous Dundigal. My name is N. Venkat Sai, rule number 23951802226. Subject Machine Learning Techniques and Practices. Topic Future Selection versus Future Extraction. Comparative role in clustering. Department Electrical and Electronics Engineering. Feature selection versus future extraction. Comparative role in clustering. Exploring the strategic choices that shape modern clustering algorithms and their impact on data analysis outcomes. Unpacking the problem. High dimensional data challenges. Modern datasets often contain hundreds or thousands of features, creating unique challenges for clustering algorithms. This phenomenon known as the curse of dimensionality causes distance between points to become less meaningful as dimensionality increases. Clustering algorithms struggle to identify genuine patterns when overwhelmed by irrelevant or reductant features. Data sparsity point become increasingly distinct in high dimensional space, making similarities measures unreliable and cluster boundaries. Computational cost, processing time, and memory requirements grow exponentially with each additional feature slowing analysis significantly. Noise amplifications. Irrelevant features introduce noise that obscure genuine patterns, reducing clustering accuracy and interrupt. Feature selections, the art of choosing the best variables. Feature selections addresses dimensionally challenges by identifying and retaining on the most informative subset of original features. Rather than creating new variables, this approach carefully examines existing features and eliminates those that contribute little to clustering performances. The result maintains interruptibility, reducing complexity. Interruptibility preserved. Selected features retain the organic meaning, making clusters characteristic easy to explain stakeholders and domain experts. Computational efficiency. Reducing features count directly, decreasing processing time to resource requirements, subsequent clustering operations. Noise reduction. Removing irrelevant features eliminates distracting signals, allowing algorithms to focus on genuine patterns. Feature selection mode filters vapors and embeddings. These distinct methodologies approaches exist for identifying optimal features, subsets each of unique strength and computational traits of. Filter methods apply statistical tests and rank features independently of clustering algorithms. Techniques include corollary analysis, check-square test, and information gain measures. Fast and computationally effective but may miss feature interactions. Wrapped methods use the clustering algorithms itself as a black box to evaluate feature subsets performances. Employ such strategies like forward selections or genetic algorithms, more accurate but computationally expensive for large datasets. Embedded methods integrate feature selection within the clustering algorithms itself. Regulations techniques like Loiseau and Radji regressions naturally syncing less important features coefficient towards zero during modern training. Feature extraction, transforming data into new representation. Feature extraction takes a fundamentally different approach by creating entirely new features that are combinations of organic variables rather than selecting for existing features. This maximum variance or meaningful patterns. Dimensional reduction. Transform high dimensional into compact representation while presenting essential structure and relationships. Pattern discovery. Relieve hidden correlations and latent factors that are not apparent in organic feature space. Noise suppression. Spread noise across multiple new dimensions by concentrating signals into fewer meaningful components. Feature attraction methods PCA, TSN, and autoencoders. Three powerful techniques dominate feature attraction, each suited to different data characteristics and analytical requirements. Principal component analysis. Linear transformer that identifies the orthogonal components capturing maximum variances. Fast, deterministic, and interpretable through Component loadings best for linear relationships in preserving global structure is essential. Distributed statistic neighbor embedded nonlinear techniques that exist at preserving local structure and relieving cluster patterns. Computationally intensive but produce excellent visualizations, idea for exploratory analysis and high dimensional data visualizations. Autoencoders, neural networks architectures that learn complex representation through recursion laws, flexible and powerful for complex patterns, can capture nonlinear relationships while scanning to massive dataset using deep learning frameworks. Impact on clustering, how each approach shapes outcomes. The choice between feature selection and extraction significantly influence clustering result, affecting both algorithm performance and interactive and discoursed patterns. Feature selection impact. Clusters characteristics direct map to organic domain concepts. Processing speed improves proportionally to dimensionally reduction. May miss complex patterns requiring features combinations. Best when domain knowledge guides features importance. Feature extraction impact. Relieve hidden pattern visible in organical feature space. Often produce trigger more distinct structures. Require additional interruptions effort for new components. Essential for high correlated or redundant features. Case studies, real world applications and the result. Healthcare diagnostics. A hospital network reduced 200 plus patients metrics to 15 principal components using PCA embedding K-means clustering to identify patient subgroups with 40% of faster processing and 25% of improved outcomes prediction accuracy. E-commerce segments, manufacturing quality, probes and cons. Decide between selection and extraction. Feature selection advantages. Interpretability. Clusters relate direct and organic features. Speed, reduced dimensionality, lowers computationally cost. Simplicity, minimum processing complexity. Domain alignment, presents business meanings. Feature extraction advantages. Pattern discovery, relieves hidden correlations. Noise robustness, speed noise across components. Flexibility, heartless complex nonlinear relationships. Comprehensive, achieve dramatically. Feature selection limitations may miss interactions required feature combinations required careful feature engineering. Feature attraction limitations. Interoperability challenges. Components lack of direct meaning. Overfitting risk may capture noise as less effective with high correlated features. Feature attraction limitations, interruptibility challenges, components lack direct meaningless computational cost, transformational adds processing time, overfitting risk may capture noise as signals. Key takeaways and best practices for your projects. Strategic features. Engineering choices significantly impact clustering success. Consider these guidelines when designing your approach. Start with feature selection. Begin with the correlation analysis and simple filters to eliminate obsessive reduceness. This quick win often reveals whether extraction is truly necessary. Second, consider interpretability requirements. When stakeholders need to understand cluster characteristics, selection often proves superior. Reserve extraction for exploratory analysis or when interpretability is secondary. Experiment with both approaches. Compare clustering result using identical algorithms on selected versus extracted features. Let empirical performance guide final decisions rather than theoretical performances. Validate with domain experts. Feature selections benefits from expert knowledge about which variable matters most. Extraction results required expect validation to ensure discovered patterns make business sense. Monitor computational budget. Large data sets favor efficient selections methods. Extraction techniques like these become empirical behind thousands of observations with while PC and auto scale more graceful. Thank you.